This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So just as a quick flashback, thanks for your patience yesterday with the tech issue. I have jumped into last year's LMS and grabbed to make up. So if you weren't in class yesterday, we couldn't present, and so I did everything on the whiteboard, which also means that whatever I did on the whiteboard wasn't captured. But I've given very similar material last year, and so I've downloaded last year's lecture capture and made it available through the LMS. If you want a different version, so the current version of the lecture capture was mostly just my voice, which doesn't help very much, particularly when you're trying to understand tables. So if you want to go through that lecture in a different way, or if you weren't here, have a look at that lecture capture. Today, the computers work. Which means that over the course of yesterday, enough people must have got in touch with tech to make it work. So we're done now with the basics, which is to say, setting the scene, setting the language so that we can start to solve problems. The last two lectures were about understanding where I might get my property information from. So there's a lecture on the ideal gas law, where it comes from, how you use it, and a couple of laws associated, Charles' law, Boyle's law. Coming down to the use of the gas constant and the state equation, the equation of state, to be able to determine the properties once you've got two independent intensive variables. Yesterday was all about using the property tables for a vapor. So if I'm changing phase, if I'm going from a liquid to a gas, I refer to that problem as as my working fluid operating as a vapor. And so for that, the equation of state is such a mess and so long and complicated, it is much, much easier and more precise because the equations that have been written down or also break down at some points to get the data from property tables. But that then forces you to do a lot of interpolation. In the beginning, I pick values that are sitting just on a row or just in a certain column so that you can just read them straight off the table. In the end, when you're doing whatever arbitrary problem you're trying to solve, you would need to take the time to work out between values. There's an exercise that we didn't get a chance to do on board, on the board yesterday at the end of last lecture, which is a two-way interpolation, which is what happens when it's not just going between two rows, but between two entire tables, and I'm trying to find a value in between. Like as I said during yesterday, the maths is not hard, but the fact that it takes a couple of steps means there's a couple of places where you can make mistakes. And so it is worth, even though it looks uninteresting, it is worth doing that on paper without looking at the notes and making sure you get the same answer to convince yourself that you've got the skills to get the properties. Each of the opportunities to practice what we're doing are on you. So you get your tutorials, you get the lectures, but outside of that time is the time where you have to put in the study to satisfy yourself that you've got the skills for solving these problems. Because the whole system's quite compact, and because the number of lectures you get are quite compact, we don't get a lot of time to practice the skills, and we don't get a lot of time, which means you don't get a lot of time to make mistakes and find out that it went wrong. So try, make the mistakes, and then see how to be extra careful when it comes to assessment and exam time. So now that framework has been laid, the next thing we go on to is this conservation of energy, which in thermodynamics is referred to as the first law of thermodynamics. and we will study it today for closed processes or closed system boundaries. And then we will go on to, that's to distinguish it from the study of flowing processes. So a turbine is a flowing process. The gas comes in one end and goes out the other end. For the purpose of our analysis, a piston cylinder is a closed process. So in a car, I understand that I've got valves that open and close to let gas in and out, but during the process that I'm interested in for compressing the fuel and air in a car engine or releasing the energy, we treat those as closed processes. And so you can use a different set of maths for the closed process and a different set of maths for the flowing process. They all come from the same place. They all come from the same understanding of the conservation of energy, and then you just cross out different terms or turn it into a rate instead of an absolute value. So let's have a look at some of this. So the reminder about the laws. We've got the first law, second law, and we came up with a couple of other ones, a zeroth law and a third law. The first law is your conservation of energy. This one, written down at its absolute purest, which is to say least immediately useful, is of a system. Remember, we defined a system boundary. We have the inside the system, and we've got the surroundings. Of a system, the difference between the energy that went in and the energy that came out, which is to say that crossed the system boundary, results in a change in the energy in the system. That looks pretty simple. It means there must be a concept of how do I measure the energy of a system, which is kind of what we do here. So we need a number, we need a unit, and we need a number to represent the energy. Temperature is not that number. Temperature doesn't have a unit of joules. We measure energy in joules. Temperature gives us an indication, a guide for the thermal energy content of something, but we miss the energy content due to pressure. We miss any nuclear energy content. We miss any chemical energy content. So we need tools to be able to evaluate what is the energy inside our system, what is the energy transfer across the boundaries. So we need to keep track of whatever work's done, any mass that's crossed over. And so this relatively simple statement up on the board of if it goes in and it doesn't come out, it stayed. Or if it went in and it all comes out, nothing changed. There's a couple of different ways to say it. That relatively simple statement sets up a whole study of thermodynamics that we need all our rules and maths for. The second law, we need the idea of entropy. We won't do that for another week and a half. So we'll mathematically define entropy so that we can then use it. And the essence of that law, that maths doesn't tell you, that equation doesn't tell you, but the essence of that law is that processes have a natural direction. And if you want them to go the other direction, you need to put extra work in. It also, another essence of that law, again, not immediately seen in the mathematics of it, is that you can never have 100% efficiency of anything. You always lose. So the first one says you can't get better than 100%. The second one says you can't even get 100%. And as I said on the very first day, there's also a zeroth law which tells you that equilibrium is equilibrium, and that's how you define temperature. And the third law that is how you prove that there is an absolute zero of temperature, which is the point at which molecules stop moving. All right. So that's just a reminder. So this lecture is broken up into thinking about heat and work. What units, what letters are we going to use, and how do we start to identify when we care about heat and work? We'll do the first law of thermodynamics, and then we'll apply them to a non-flow or a closed process. The ideas of work, which is to say energy used to change something, are things you've been playing with since high school physics, and then through the last few years. So simple mechanical work of applying a force and moving an object over some distance, F times x, is our basic unit. Again, inside that maths is the idea of I use some energy to make a change in my system. If that system were conserved, I've pushed something from one end of the desk to the other. At some point, that thing's going to stop because I've got friction on my desk. If I drew a nice little system bubble where no energy could cross over my system bubble, the whole area would get hotter because I put some energy in. I did some work on the system, and if I don't let that energy out again, it's got to stay inside the system. So the fact that my block, whatever it was that I was pushing a computer across the desk, the fact that it stopped means there was some friction. The fact that there was friction means there's some heat. The energy I put into the system by pushing that computer stays in my system unless I let heat transfer across my system boundary to let the temperature equilibrate with the room. So we keep track of the work we do, and we come up with a bunch of units as well. First things first, we need a measure of the energy. And so we need a word for it and a letter for it. And it needs to be in joules because that's our unit for energy. We call it internal energy. The one we use most of all we call internal energy, and it has the letter or the symbol U. And its job is to add up all those things I said before. Your thermal energy, which in thermodynamics is referred to as the sensible energy. This bit I don't know why. I have no idea what the connection with the word sensible. Maybe it's you can sense it. I've never found out why on earth they would call thermal energy sensible energy. The latent energy, the phase change energy, the chemical energy in the bonds of the molecules, and the nuclear energy in the atoms itself. Every time I do a thermodynamic analysis, I'm representing, in the units I'm using and in the tools I'm using, I'm representing all of that. But we have one wonderful short circuit to having to keep track of all of the energy in chemical bonds and all of the energy in the nuclear forces and all of the energy in the latent heat. And the wonderful short circuit that we have to this, or shortcut, is that I am only interested in change. And so if I don't burn anything, if I don't release any chemical energy or add any chemical energy, the delta between state 1 and state 2 results in no change in the chemical energy. That term I can ignore for my problem. If I don't release any nuclear energy, same. If I don't change phase, then all I'm interested in is my change in temperature. If I don't change temperature, I've got no problem to analyze. So because we deal with changes and state 1 to state 2, a lot of the mathematical trickiness of our problem vanishes because we can just cross it off. I put this up on day 5 now. I put this up on day 5, but in the beginning, as with many of the other things I introduce, you must know these ideas are inside the term. When I say internal energy, the unit means all the energy of the system. Its job is to keep track of that, so that if I put some heat or some work into a system, I can have some kind of counter, some kind of metric to keep track of that. We have kinetic energy, potential energy, kinetic energy and potential energy as my major sources of energy. Kinetic energy is my energy from motion, which is to say, if I have a velocity, I have energy. If I have a velocity and a mass, then I have energy I need to keep track of, which is my momentum, and that is in the units of kilojoules. Hooray, good, we can use it. My potential energy, mass times gravity times z, some height above some reference. So it means, again, I need some reference point to be measuring my height. Potential energy, mass times gravity times z. Again, not new terms, not new ideas, but I'm not going to pick my coffee cup up, but if I pick my pen up, I've put some work into my system. Now my pen has some potential energy. It's not moving. It's got no kinetic energy, apart from whatever the atoms are doing because of its temperature. And then I change my system boundary. It turns that potential energy into motion, kinetic energy. The fact you could hear it drop, or that potential, or that kinetic energy had to be released. Things got a little bit warmer down there, not much because there was not a lot of energy. And you could hear the click as it hit the ground. That's released some energy out to you as well. So the system needed to dissipate the energy out of whatever boundary I've drawn. If I drew the boundary of the room, nothing's happened, nothing's changed. So if I drew a boundary of an isolated system of this room, in those few seconds that I've been talking and dropping a pen, literally nothing has changed in the internal energy of this room. So we put it all together. We put together my internal energy, my kinetic energy, and my potential energy as the energy of my system. So I need to keep track of all of those things, and then I put in symbols U, mv squared on 2, mgz. And I was saying before, as I started to introduce our units and our concept of intensive properties, we usually solve our problems on a per mass basis, which means I divide through by mass, which means that I can drop out this mass and this mass. And in thermo, whenever we drop the mass and whenever we're dealing with intensive properties, we use little letters instead of capital letters. This code is accepted and known and understood. So if you're in this field, if you're in this topic and you use a little letter, you are telling the person reading it, I am using an intensive property. If you use a big letter, you are telling the person reading it, I am using the extensive property. So the total. Which means you need to keep track of your handwriting, because little U's and big U's are tricky. They look basically the same, depending on how far away you're standing. So, we said we had system boundaries. We said they could be closed or open. In a closed system boundary, I can't transfer mass. All system boundaries, I can have heat transfer across unless I tell you it's insulated. But also importantly, all system boundaries, we can transfer work across it. If I couldn't, we really wouldn't have that many problems to analyze. Either I couldn't get work out of a system or I couldn't put work in to make a change. So our system boundary has two portals through which I can make a difference to it. I have my system boundary of a car engine. I could add heat to it, and I'm expecting the gas to start to expand and push on a piston. I have a turbine problem. I could extract work from that through the turbine and connect it to a shaft. So it means we need to understand the heat transfer part is relatively straightforward. If I have a delta T between my system and the outside world, there will be a heat transfer. The work, we need all the things we've ever learned about how work can be done, whether it be electrical work, thermal work, mechanical work, rotation work. All those equations that you've seen over the years are necessary and useful, and I will assume that you know stuff, but in the beginning I'm going to put them up so that you don't have to go hunting for it. I've forgotten how I turn rotational work into kilojoules, etc. Now, this bit I'm compelled to put up. I'm compelled to put up because a lot of thermodynamic textbooks say that there is a system convention, a sign convention. So I need to keep track of stuff. I need to keep track of whether it's going up or down. And our up or down is our minus or plus. And so what we usually say is, if I'm putting heat into a system, and if I'm taking work out of a system, I'll call those positive. I've found an easier way to do this, which is to never assume anything and just keep track of all the positives and negatives and then cross them off as I work out which ones are zeros. It's kind of like, it's the boring way. It's kind of like doing Sudoku with every single number written down and every single possibility. This thing is up there because it's in all the thermo textbooks. And so if you're reading a thermo textbook and you see positive work, it means work came out of the system. It means the system energy has gone down. If you see positive heat transfer, it means the system energy has gone up. So it's worth knowing, even though mathematically I get scared of making assumptions like that and I try to keep track of all the minuses and pluses. Okay, we get some forms of work. Electrical work, mechanical work, shaft work, spring work. If electrical power is VI, what's electrical work? You guys just done following? What's the energy done by an electrical system? What's the hard bit of? Anyway, look, I could torture you. I just realised, as I'm about to sit here staring into a bunch of faces going, please don't make me say anything. And given also that you've got access to the notes, mechanical works, force times distance, shaft work, all of this stuff is what was the force applied to over what was the hard thing to do. So, the work part doesn't have time in it. Current is a flow which has a time in it, and so I need to get rid of the time. I need to apply my power over an amount of time. So if electrical power is VI, the work is how long did you run that power for? So times it by time. The mechanical work, S or X, I don't mind which unit you use for distance, force times distance. So I've got my force, and I need to push something. This term doesn't have a time term in it. Work doesn't have a time term in it. Work is an amount of energy, not a power, not a rate of energy change. The shaft work is also force times distance, but we have a circle, and so my force in a shaft system is torque, and if I have the radius of my circle, I can work out how far I've used that torque. So I've got my 2 pi r. The n is the number of revolutions. Right? So again, I'm not talking about a rate. I'm not talking about an RPM, rates per minute, revs per minute. I'm talking about the total number of revolutions. And the spring work is the integral of the state property. So half k x squared, delta x squared, basically. Now, will I examine you on trying to memorize equations for work? No, because it's boring for me. I'm trying to teach you a different set of skills. This is physics and mechanics and electrical stuff, and I've got enough skills to teach you, or enough skills that I want you to practice and learn. I'm going to sit there with a question saying, please write down the equation for the work of an electrical thing. By the time we're well into our questions, I mean, the tutorial problems may play around with some of these ideas, right? Just to freshen them up in your mind. By the time we get to the proper end, the hard end of doing thermo, I'm much more interested in whether or not you've understood the first and second law and testing whether or not you can understand one particular cycle. So this is up there as a refresher, as a reminder of all the different ways that work can be done by a system. If these were coming out of a system, if my system produced electrical work, if my system produced mechanical work, I would count them as positive work, and I would count them as a reduction in the energy inside the system boundary. This guy is a pretty important system. We use piston cylinders for a couple of reasons, and one of the reasons we use piston cylinders is because they have some nice properties. The force that comes from my piston is being exerted by what? If I try to push that, if this system tries to push that piston to the right, what's pushing? I heard a whisper like a breath on the wind. The pressure of, or it could be a hydraulic cylinder, the pressure of the working fluid, whatever it happens to be. So I've got pressure, and for it to be turned into a force, I need to know what area it acted over. So force is pressure times area, and I move it by dx. So now I'm trying to turn this force term over dx into something I can use to analyze this system. I'd like it if there's a way to talk about the system without having to know the diameter of my cylinder. Just because sometimes it's hard to measure, and there's other things I'd like to know. The pressure's pretty easy to measure. The force is not so easy to measure. Imagine my cylinder is inside my car. So we're going to play a couple of little derivation games to cross off some terms. I'll get them up. My unit work is that force, PA, over a distance. Yeah? So PA dx. And I'm going to magically wave my hand and say that that's P dV. I'm hoping that that's not tricky. I'm hoping you look at that and go, okay. Just in case, and I don't mean this as in any way condescending, but just in case it is tricky, we've just done force, which is PA dx. This is work. Zoom in. This guy is work. PA dx, pressure times area times dx on this cylinder. The A is not changing, so the area is the same no matter how far I push that cylinder. This guy together, my area times a little change in distance, is the change in the volume of the system. So it really is no magic to then write P dV. Normally, we try to break out terms. We try to get rid of our constants and move them away. But because it's, if I imagine, what I'm trying to do with the thermo tools is build up tools where the thing that I need to measure is measurable and easily measurable. Now, I know if I made the engine, I'd know the diameter of the cylinder. In an engine, the volume displacement is something that I can work out because I can have a look at how much gas went in and how much gas went out. These are things that I can understand well. And also, more importantly for this guy, I operate on a per mass basis, which means that I can write the per mass work done as P d change in specific volume. This is now in terms of two intensive independent properties, which means I have an expression for work in thermodynamically useful units. Pressure is something I can measure quite nicely. So pressure gauges work. My little change in specific volume is actually something that is, by expressing the problem in intensive independent properties, I'm expressing it in terms of the state of the system. Expressing it in terms of area doesn't actually help me in terms of determining the state of the system, and I can't divide area by mass and say my area per unit mass. These are not things that define the working fluid. But the specific volume of the working fluid and the pressure define the energy inside that system, which means now I have a way to express the work done that is in the same language as how I think about energy. So even though it looks like a trivial change of units or change of integratable variable, we do it because our life gets easier having done that swap. It's so much nicer having the computer work. We're back up. Good. Okay. So V is the volume the system expands, and now that I have a nice differential term, I can integrate it. We do a lot of integration in the subject. Sometimes we do it quickly because things are constant, and I can just say, well, that's the difference by this times by whatever. Sometimes I actually need to keep track of the integral. And please freshen up a couple of basic integrations in your mind, particularly the one on x integral that turns into a log. That one comes up. So be prepared to do that integral. So my work done is the integral of P dV. If it were a constant pressure process, my pressure would come out of that integral, and I would just say my work done is the pressure times my change in volume. But if I don't know that it's a constant pressure process, it doesn't matter. There's a really, really important thing that pops out of this. Every time we set up a new set of tools, it's to make our life easier and make our analysis easier. What I now have is an expression that the integral of P dV is the area under a line. Now, the integral on a graph, if I have a curve and I integrate, I'm getting the area under the curve. Which means that on my PV diagram, the area under the process path is the work done by the system. That's another neat result. At this point, I don't need any more thermodynamics. I just need to be able to colour in squares on a piece of graph paper to be able to work out the work done by that curve. I don't even need to know mathematically what that curve was. I can tell you what work was done by that system by colouring in the space underneath the graph paper. If I went back again to some other state, the difference between the areas of the two graphs would give me the change in work, would give me the change in the energy of the system. Then if I had some thermo, I could tell you what the final temperature was. Because if I knew the state, if I have two properties, it's a PV diagram. I have two independent, as soon as I've got a dot on that graph, I have all the other properties of the system. So, by one tiny little mathematical change on this force times area times dx, now I have an expression for work that is suddenly useful in a thermodynamic sense. So one of the reasons why I like this subject is as you do the hard work, your life gets easier, which is a strange result, but there was a point to it all. The other connection I want to make, the major property diagrams that we use them because they make our analysis easier. This guy we use because the area under the curve is work. The TS diagram, we'll come to later, temperature and entropy, seems like a weird combination. We use it because the area under that guy is heat transfer. So there are two, these two property diagrams will become our friends all the way through this subject and beyond. All right, so now we've defined work, we've talked about heat transfer, we've come up with an expression for work which will come up time and time again. We've turned it into units that are our friends. And so then we move on to the first law. Now, I've already waved my hand at the first law. There are many, many sentences one can use to describe the first law. And the extra step I'm going to take, so we've done energy is conserved, and mostly people are accepting that. And now we've spoken about what I mean by energy, how am I going to measure it inside my system, what unit am I going to use, how am I going to describe energy. Right, so energy is conserved. I keep track of the heat and the work that crosses the system boundary so I can know what changed. There is an extra thing. I don't know if you remember on very day one where I introduced this guy, Sadi Carnot, and he was interested in what was the maximum efficiency I could get out of an engine. For a unit of heat input, what's the maximum work I could get out? In his development of this analysis, one of the pieces of magic he came up with was realizing that most things end up where they started. Which is to say, a piston cylinder in a car engine, imagine, even over a four-stroke, goes up and down and up and down. At some point it got hot, at some point it got high pressure, at some point it expanded. Eventually it filled back up with the same thing it started. So if I were to track, at any point in time, if I were to track that guy around on a state diagram, wherever it went, I know at some point, no matter what's happened, whoop, my cycle is complete and I'm starting again. A gas turbine doesn't look like a loop, but always coming in the front end is cold air. Whatever it is, whatever magic happened through the compressor, through the combustor, through the turbine and out the exhaust will cool back down to cold air again. And if I draw a little dotted line from the cold air outside world all the way back to the front of the engine, that was atmospheric and room temperature. Well, we're up in the sky, so cold, and not atmospheric anymore. Anyway, it was a certain condition, comes back in at that same condition. The art of using this cycle concept brings a really, really nice thing. If I come back to the same point on the PV, the same point on the PV diagram, the same two intensive independent properties, I'm back at the same state, which means that my energy has not changed. Whatever it is that went on with heat transfer and work, by the time I'm back here, I'm back at the same energy that I was. So if I follow that whole loop around, my conservation of energy says that whatever it is needed to balance out. Whatever processes went on in the thermodynamic cycle needed to equal each other so that when I'm back at the start again, I have no change in my system. It's almost a trivial result, except that it's a really powerful simplification of our mathematics. So a system undergoes a cycle, and the net energy transferred into the system during the cycle as heat is equal to the net energy transferred out as work. The work might not always be useful, which is why we have the concept of efficiency. There is work to be done in overcoming friction. There is work to be done in producing sound. Also, I put some heat in, some of it came out again. So the net heat transfer, not the heat I put in, but the net heat transfer. I probably lost some heat as well. I released, in my piston cylinder that had some combustion in there, I released a whole bunch of chemical energy heat. But I also have this really hot car engine with oil flowing through it to keep it cool. I am taking heat out of it all the time. So it's the net heat transfer into the system needed to come out again because I came back to the same point, the same energy state. So if I put energy in, it had to come out, which means if I knew the total heat transfer, I know how much work my system did in a cycle. If I know how much work my system did in a cycle, I know the heat transfer, the net heat transfer. So that lays the foundation of the building blocks of how we proceed on the thermodynamic analysis. Because sometimes it's a sleuth work problem, but it's one where you know the shape of the puzzle. You're trying to solve a puzzle, but you know exactly the shape of the puzzle and you know your start and finish point. So if I know exactly how much fuel I burnt, I know the heat transfer in. If I know how much work came out and how hard it was to push, which is the work I put in, so I pushed, I released some heat, and then it pushed, I know how far the car went. The last bit, the heat transfer out, maybe I didn't measure that. Maybe there was radiation heat that was really hard to monitor, but it's the only missing piece of the puzzle because I came back to the same place. So I can now estimate, no, not estimate, I can calculate the heat transfer out of my system and complete every single process path. I would do that. Why would I bother to do that? The heat that's gone out is wasted energy. If I want to improve the efficiency of my system, I need to know what did I lose. Now, I can't change the fact that the cycle comes back to the same point, but I can change how efficient that process was, how much I gained versus how much I lost. So, one of the things I've learned is the integral symbol tends to shut people down. The next thing I've learned is the integral symbol with a circle drawn in it absolutely shuts people down because you never actually mathematically use it. It's just shorthand for saying if I follow the path around a cycle. So everything I've just said in words is exactly that maths. And I will never ask you to write down an integral symbol over a loop in this class because I don't want your brains to shut down. And again, not trying to be condescending, it's just my observation of my own behavior with integral symbols and path integrals. I just want to say that that is how you would express it. And the reason why I show that to you is in case you're ever not listening to me and learning thermodynamics. You'll see it written down and go, oh, that's just keeping track of everything on my cycle. And so if I knew 1 step, 2 steps, 3 steps, 4 steps, I can do that. Because a path integral doesn't need to be the whole maths all the way around. You break it up into pieces and say this is equivalent to this bit, this bit, this bit, this bit. All right, so all the changes in heat transfer have to equal all the changes in work transfer for a cycle. So we do split it out. And if I follow path A down to 2, and I follow B or C back to 1, so this is 1A to 2, and from 2 along B to 1, 1A to 2, 2C to 1, they all equal the work and the heat transfer. This is on left-hand side is a statement around the work, right-hand side is a statement around, left-hand side is a statement on the heat transfer, the right-hand side is a statement on the work. I write it all down, they have to equal each other. And so what I can say is that the difference between the heat and work transfer for path B is the same as the difference between the heat and work transfer for path C. Also should make sense because if I'm ending up at a state, the state is the state is the state. Doesn't matter what wobbly line point 1 is defined as a certain amount of energy, point 2 is defined as a certain amount of energy. So the difference between the heat and the work tells me it must be the same no matter the path. Again, think about that. What it means is I now have a choice. The path I follow to get to a state, I have a choice to make about how much heat transfer versus how much work results in that energy change. The total energy change is fixed. If I want to move from point 1 to point 2, I know the total change in energy. But by choosing different processes, I can control whether that was all done by heat or all done by work, or some combination in between. And that's where you design better thermodynamic processes. If the amount of heat to get somewhere, if it's all heat, maybe that's easier to set up than if it was all work. Maybe the work is easier to set up. Maybe I have no control and it has to be some combo. I know that the end state is the same energy level. All right, so that's the build-up to what we now have as the non-flow energy equations. What we do, what is up there is the conservation of energy, and it's written now with the difference between the heat transfer and the work done is the change in the energy of my system. So, I'm going to write that in another way. No, not so much in another way, just again. We started with E in minus E out equals delta E. We said we like to work on intensive units, so divide through by mass. I can use little e in minus little e out equals delta little e. We said we measure system energy with my internal energy, my kinetic energy, my potential energy. So for the moment, let's just leave this guy as it is. Let's have a look at this and this. I said by convention, I'm going to say that work done by the system and heat transfer into the system are my positive ones. The minus is there. So for this guy to be positive and this guy to be positive, that minus is there just because it's delta E. It's a change. So the minus stays there. This goes Q. I don't write Q in. If I leave it as a positive Q, that is heat transfer into the system. Minus work. I don't write work out because this guy here, if I just write work and I leave it as a positive, I understand there's a minus there. Bear with me. If I leave this guy as a positive, I'm saying the work out of the system equals delta E. At that point, if I take, sorry, my deltas aren't very good, they're more like circles. At that point, if I take my E and split it all out to all the terms that we talked about before, U plus, this is delta U, actually, let's write this as delta everything. Delta U plus KE plus GZ, plus PE. With me? That's all the terms, all the ideas for energy, which means I can write that delta U plus V squared on 2 plus GZ. Or I could split that out to delta U, delta V squared on 2, delta GZ. I would do that split, so delta U plus delta V squared on 2 plus delta GZ. I do that split because, as I was saying before, we make our life easy when we realize that we're interested in the change of a system. If my box, my system boundary, doesn't move up or down, there's been no change to the potential energy. Maybe the bits in between have moved around, but I don't care. I'm talking about the system. The energy of my system. Remember I was saying outside the system boundary, I don't care. Inside the system boundary, I don't really care, provided I know what happened. So what I'm interested in is, did the system boundary move up or down? Am I following a falling waterfall? Some kind of change of potential energy? Am I following an elevator? This guy goes to 0. If my box, if if what's going on inside my system hasn't really accelerated or decelerated, then I have no change in my kinetic energy. So the system may be going at a crazy speed, maybe a huge velocity. If it's not changing, there's no change in the kinetic energy. If I don't change temperature, if I don't change phase, if I don't release nuclear energy, if I don't burn anything, and I don't change temperature, which is the main thing that controls my sensible energy, so sensible, latent, chemical, nuclear, if none of those change, this whole side goes to zero. There has been no change in the system. Which doesn't mean that nothing happened, but it means that anything that happened as a complete balance between work and heat transfer. So if the system energy did not change, the heat that went in came out as work. So the maths that is relatively simple and kind of uninformative turns into terms that let us imagine how would I solve lots of different types of problems. Okay. Delta E can be thought of as a stored energy, internal energy. A lot of this is the words of what I just told to you. And so then we write that as this. Those equations, so if I say, note that line, if we ignore the kinetic and potential energies, then we can just write Q minus W equals delta U. That is the non-flow energy equation. Non-flow because I've got no mass flow rate included in the terms. I'm talking about energy, not power. We'll come to that on Friday. If you were to start solving a problem saying, identify that this problem is a non-flow problem and I am going to apply the first law non-flow energy equations, you could begin by writing that down and you're good to go. Again, I'm in the habit, because I've made so many mistakes over my life, I'm in the habit of writing down the first law is E in minus E out equals delta E, and now I'm going to cancel these terms so that when you read my work, you can see exactly what I was thinking. So that's what I just said a couple of times. If we neglect connection with potential energy, in fact, this is the slide of all the words I just used. So I put them up. I put them up in case I speak too fast, or in case you learn better by reading than by listening to me talk. Okay. So this is now a little bit of history on proving some of this, on how people got to the stage of saying energy is conserved. Because until you keep track of everything, it's very difficult to actually prove it. So you've got to have perfect insulation, etc. Now, you remember I said that this beer brewer, so one of his major things, the industrialist who makes beer, got in trouble in the scientific community because he connected the idea of work and heat. And people didn't like that. They weren't willing to accept the idea that there was any connection between temperature, heat, and motion, kinetic energy, work. So what he did was, there is work done when you allow pressures to equilibrate. A thermometer inside a bath, substance of a perfect gas. If the temperature changed, then the internal energy of the system changed. So he's able to keep track of all the temperature, motion, and all the work. The Q, perfect insulation, Q equals 0. 0 work done to the system, in or out of the system. And then he saw no change in temperature. And so there's an extra law that came out of this. And this is one we use in a perfect gas. The energy content, the sensible energy content, which we call internal energy, is defined by temperature. If I tell you the temperature of a perfect gas, I have told you its internal energy. That's powerful because temperature is easy to measure. I didn't need to measure the pressure or the volume of the perfect gas. That's very, very powerful maths. Experimentally, that's super powerful. Because particularly in a changing system, volume is hard to measure. Temperature is easy to measure. So for closed processes, oh, good. Excellent, excellent. Sorry, tapping through these, and I was thinking, I haven't told you guys about specific heat yet. Now that we've got all of that, I want to keep track of where my energy went, and I want to keep track of how do I connect. This is the useful bit. Temperature, internal energy. Temperature, Kelvin, internal energy, joules or kilojoules, not instinctively connected. So I need a thing, an idea, to be able to connect temperature and internal energy. I need a way to connect how much does my energy of my system alter if I change its temperature. Because I can measure temperature, and I can't measure internal energy. I can't measure it easily. So we have this idea called specific heat. Specific heat is the amount of energy required to raise a kilo of something by a degree. So Kelvin or Celsius, doesn't matter. Which means it has a nice little delta. And there is two ways that I could change the temperature of something. I could add some heat to it in a constant volume, or I could add some heat to it in a constant pressure. I end up, therefore, with an idea of specific heat at a constant volume, CV, specific heat at a constant pressure, CP. We will play with them. The isochoric one tells me the change in internal energy for the change in temperature. So CV is this partial differential at a constant volume, du for dt. If I change my temperature, I change my energy. CP does the same thing, the same idea, but a constant pressure. So we're going to do CV. I'm now starting to talk quickly because I'm conscious I've got 4 minutes of your attention and also of the recording. With an isochoric process, constant volume. I go up and down on the PV diagram, just straight up and down. Up and down. Now, what was the area under the graph for a PV? 0. That's specific to this. What does it represent? Well. All right, so this process has no work. Yep. I'm interested in changes in temperature for changes in internal energy for changes in temperature. I'm going to assume something happened with temperature and something happened with heat transfer, but it has no work is done in this process, which is why we use it for definitions. So work, area under the graph equals 0, and then from the non-flow equations, all I've got is Q is equal to change in energy. I've dropped Q minus W equals delta U. If work is 0, I've got Q equals delta U. All right? So for a small step, dQ equals du. The change in heat transfer equals the change in internal energy. If I take my definition of CV, so at the moment I haven't really done anything. I've just said, let's allow a concept to exist that says this letter CV is the change in internal energy for the change in temperature. If I plug that in, I get dQ equals CV dt. All partial differential on dt just there. I could go look up the internal energy, but for a perfect gas, I've got an extra thing. Apply Joule's law. Joule's law said this connection, internal energy, is connected only to temperature for a perfect gas, for an ideal gas. So CV equals now no longer partial differential, CV equals du dt, full differential. If I had the constant specific heat, I could now connect internal energy to temperature through this equation, right? So I'd have U equals CVT if I knew the CV, with a constant, which also means that if I'm doing a delta, the constant will disappear. Yeah? And that's the useful, that's the powerful thing. My delta U will be CV delta T, because the CV stays the same. All right? That bit there, for a perfect gas, an ideal gas, this is the big flag. Don't use this for steam. For an ideal gas, du, if I have the change in temperature, I have the change in internal energy. That message doesn't require that I have an isochoric process. The CV definition came from thinking about an isochoric process, but now that I have the idea, I can use this for an ideal gas regardless of what's going on. du equals CV dt. We will use that a lot. I'll leave that. So all I do here is saying, so on Friday, we will do examples. Basically, Friday is an examples day. The examples are already up. The work solutions are already up.